So, we have seen that a dislocation cannot end abruptly inside a crystal, but it can do one of these things. It can end on external free surface, we have looked at that, and it can end on an internal grain boundaries. This was also we have looked at. In this video, we will look at this option, which is a dislocation line can end on other dislocations and form a node. So, these dislocation node is the topic of discussion now. I have been drawing for you many times a slip plane and dividing the slip plane into two regions, slip and not slip, by a line which becomes our dislocation line. One side of the line is slip and the other side is not slipped. So, I call it slip and no slip regions. Now, it is not necessary that only one dislocation runs throughout the crystal on a given slip plane. So, if I have a slip plane and then I divide it, if I divide the plane into more than one regions, let me say, instead of 2, now I have divided into 3 regions. So, I have drawn 3 lines. Each of these lines can be a dislocation line meeting at a common point, and that common point will now be called a node. So, this is a node, this is, let us call dislocation 1, a dislocation 2, and this is dislocation 3. So, 3 dislocations are meeting at that node. So, this dislocation line, which is a dislocation 1, is starting on a free surface, but is not ending on a free surface. It is not ending on a grain boundary also, but it is ending on other dislocations. So, this possibility is also there, and in that case we get such point, junction point, which are called node. So, we can call one of these regions, let us say, as a no slip region. So, let me call this as a no slip region. So, which means if I cross dislocation line 1, I will come to a slip region. So, this will be slip 1. But now, when I cross dislocation line 3, again there should be a slip. If this region was also slip 1, then there will be no differential slip between these two regions, and this boundary or this dislocation line 3, will disappear. So, there has to be some extra slip, some differential slip as I cross this line. So, this region will be having a different slip, and let me call that a slip 2. And corresponding to these slips, all these lines will have Burgess vector, as you know, and the Burgess vector, according to our convention, also depends on the line vector. So, the convention for the node is to take all the line vectors going either out of the node or coming into the node. So, let me take all the line vectors, the T1, T2, sorry T3 and T2 coming out of the node. I could have taken all of them inside the node also. So, in the node the convention is, let us write down, at a node take all T vectors the tangent vector or the line vector, T vectors either pointing away from the node as shown here, or pointing into the node. And based on these T vectors, you determine their Burgess vector. So, each of them will then have some Burgess vector associated with the dislocation line. So, let me call this Burgess vector B1, this Burgess vector B3, and this Burgess vector B2. So, all the dislocation line will have the corresponding Burgess vectors. And the interesting thing is that, and that is called Frank's rule, that the sum of Burgess vectors at the node has to be 0. If you follow this convention, then sum of all Burgess vectors at the node will be 0. This is easy to intuitively see, although we are not giving exact proof, but you can intuitively see. Suppose we start from the no slip region, then as I cross this dislocation line 1, then I undergo a slip 1, and the slip is by amount given by the Burgess vector B1. So, this region is slipped by a vector B1 with respect to the no slip region. As I cross this dislocation line 3 now, I get a further slip of Burgess vector B3. So, now the total slip of the region 2 with respect to the starting region, which was no slip region, is B1 plus B3, sorry, B3, B1 plus B3. Now, when I cross from this region to the no slip region, I again undergo another slip which is now equal to the amount B2. So, when I come back to original no slip region, I have undergone a slip B1 plus slip B3 plus slip B2. But since I am back to the original, the sum of all these 3 should total to no slip, because finally I am in a no slip region. So, the sum of B1 plus B2 plus B3 in this case should be 0. So, in this case B1 plus B2 plus B3 should be 0. So, this is an important rule to keep in mind, but the validity of the rule will depend on this convention. So, if you take your T vectors arbitrarily, then obviously this will not be satisfied. So, it is important to keep in mind that at the node, either you have to take all the T vectors going out or all the T vectors coming into the node. Then you will have this Frank's rule, that the sum of the Burgess vector at the node will be 0. I have shown you here a planar network, but the network in real crystals can be 3-dimensional also. So, the third dislocation line need not be lying in the same plane of the paper, but may be moving out of the plane of the paper. In that case also, this rule will be true.